Okay, so mostly we've been talking about the shortwave radio spectrum, wavelengths, say between 80 and 10 meters. I think it's time to go low. This is what I call the limbo session of the HamSCI conference. We're going to talk about low frequency and actually VLF, very low frequencies. Here is Jonathan Rizzo, KC3EEY.
Hi everybody. As Gary said, my name is Jonathan Rizzo, KC3EEY. I'm a VLF natural radio enthusiast and electrical engineer. After more than 2 years, the VLF reception system installed at the W2NAF-KC3EEY VLF Observatory in Springbrook Township, Pennsylvania, has proven an essential tool in ionospheric and magnetospheric research. Using low-cost and simplistic hardware like a VLF active antenna, Raspberry Pi, sound card, and GNSS receiver, along with powerful open-source software such as VLF-RX tools and GPS daemon, it's possible to capture VLF spectrum data with science-grade accuracy, precision, and reliability that an amateur can easily achieve. Building on this foundation, new developments were made possible in research, analysis, and system improvement. These developments coincide with a call to establish the HamSCI VLF network, a network of worldwide VLF reception systems installed and operated by volunteers, amateurs, and professionals alike in radio quiet locations. The HamSCI VLF network will augment the existing HamSCI experiments with D&E layer, ionospheric phenomena, lightning location data with accurate stroke solutions, and more. The VLF reception system consists of a VLF active antenna and back-end processor. The VLF active antenna is an E-field probe with integrated preamplifier, all encased in a PVC pipe. It uses a Cat6 feed line, one pair for power, the other for signal, which is fed back to the back-end processor. The back-end processor consists of a VLF active antenna interface, Raspberry Pi, audio injector stereo sound card, and GNSS timing receiver. The Raspberry Pi runs open source software like VLF-RX tools, which is an SDR processing toolkit, and GPS daemon. Because the system uses open source software and off-the-shelf hardware, the cost is extremely low, making it possible for volunteers and amateurs to build and install these systems in radio quiet locations. This is the inside of the VLF active antenna. On the left is a picture of the VLF receiver preamp board constructed using Manhattan construction. In the middle, you can see the board fits inside a foam insert. On the right, the E-field antenna is comprised of copper tape on the outside of a foam insert. The antenna wires solder directly to the copper tape and the front-end input of the VLF preamp. The foam insert is used to dampen microphonic vibrations due to wind. The Cat6 pairs and earth-ground connection attached to the green screw terminal connector, and everything fits nicely in the pipe. This is the back-end processor. It contains an isolated DC to DC converter, an audio isolation transformer, main power converter, Trimble Res SMT360 GNSS timing receiver, audio injector stereo sound card, and a Raspberry Pi 3. Spectrum data is stored and streamed over the internet to an aggregation server where you can listen to the VLF receiver in real time, look at captured events from the event detector, and see plots of the VLF power spectrum. Here's some examples of natural radio emissions captured by the system. One of the primary signals of interest are natural radio emissions like whistlers. Whistlers are lightning spherics that propagate through magnetospheric ducts. The electron density of the ducts causes the characteristic dispersion seen in the spectrogram. These whistlers were captured March 12th. Let's see if I could get them to play. Oh.
We may have trouble.
Oh, okay.
Yeah. Sorry. You may have trouble with that.
Okay. Okay, I apologize, but these are the spectrograms, and if you're interested in the audio samples, please see me. Another signal of interest is dawn chorus. These are periodic emissions originating in the magnetosphere and arise through complex plasma interactions. These are samples from a 2-hour-long dawn chorus event that occurred November 6, 2023. Again, if you're interested in the audio samples, please come see me.
I might be able to
Oh,
try one thing.
perfect. Here are the whistlers. A great feature of VLF-RX tools is streaming of compressed timestamp of VLF spectrum over a local network or the internet, enabling processing on other servers and systems, and is great for processing spectrum data from a network of VLF receivers. The author of VLF-RX tools, Paul Nicholson, runs a data processing server for a network of his VLF receivers. The VLF reception system uplinks spectrum data to this server via a compressed Vorbis stream over the internet with the bandwidth of 16 kilohertz audio bandwidth. On this website, you can see a list of contributing VLF systems, including this system in Springbrook Township, Pennsylvania. Clicking on the details link opens up a page with some captured events, signal information, power spectrum, amplitude histogram, and received alpha F1 frequency spectrum, as well as a link to listen live. Clicking the events link brings you to the event gallery, which shows a gallery of event spectrograms. Here, many Whistler events from 2022 are shown. Clicking on each thumbnail will bring you to a page to view a larger spectrogram and listen to the event. There is even more information. Clicking on the cross-correlation link will show you a cross-correlation plot with peak correlation between the VLF reception system and another installed in Forest, Virginia. On the right is a map containing locations of each VLF receiver as well as their geomagnetic conjugate points. New in development is a 3-channel back-end processor. This allows 3 channels from 3 different VLF receivers to be captured and processed. In this setup, an E-field receiver as well as a dual-channel orthogonal loop H-field receiver would be connected for triple axis reception. Please see my demo and poster on Saturday for more information. Also in development is a 2-channel H-field receiver. It utilizes an LT1028 front end and an LT1010 line driver. It's 2 channels for a north, south, and east-west loop orientations. It runs on 24 volts power. It uses an isolated DC to DC converter and 2 audio isolation transformers. 3-turn orthogonal loops using 14-gauge Romax wire, and is used in conjunction with an E-field probe VLF receiver for triple axis reception. There have been recent developments in amateur transmissions in the VLF band, specifically transmissions at 8.270 kilohertz. using a new mode called the EBNOT mode. Using powerful error correction and GNSS reference signals, it's possible to send messages of a few characters or more, opening up the VLF band for use. This is an EBNOT transmission rig, partially assembled. And it consists of a Raspberry Pi running EBSynth and EBNOT software, which is developed by the author of VLFRX tools. It uses an audio injector stereo sound card and GNSS receiver to generate a GNSS locked carrier and coherent BPSK modulation. The output is then fed into a separate audio amplifier and earth probe antenna. On the remote end, the VLF reception system is used to capture and process the signal. Then it's fed into a decoder. Data from the VLF reception system was provided to student Matthew Woodward and Dr. Morris Cohen of Georgia Tech's LF Radio Lab. Using a technique they developed, amplitude data from both NAA and NAU, those are Navy VLF transmitters, on the day before, on, and after the Tonga eruption was analyzed for the possibility of atmospheric gravity waves. There's a strong indication in NAU's amplitude data of an atmospheric gravity wave shortly after the Tonga eruption. These plots are 6 minutes in duration and indicate possible gravity wave at 0.02 hertz. On the day of the 2023 annular eclipse, a Class C solar flare occurred at around 1630 UT, roughly around the same time as the eclipse. Observations in the VLF band indicate combined effects of the solar flare and the moon shadow. An increase in signal amplitude was observed in the U.S. Navy VLF transmitter NAA as a gradual peak. That's the bottom stacked plot where the arrow is. A phase change also occurred, indicating a change in VLF propagation characteristics of the Earth ionosphere waveguide. That's the top plot. The stacked plot on the right shows these observations in greater temporal detail. These are compressed spectrograms for the whole day of lightning spherics. On that day, decreased absorption was observed in lightning spherics during the eclipse duration, showing a similar gradual peak. An analysis of WWV amplitude and phase data by Steve Serwin, WA5FRF, he found that nulls in received signal amplitude occurred at dawn and dusk of the local diurnal day, along with 180-degree phase shifts. This phenomena occurs on all VLF waves propagating through the Earth ionosphere waveguide, including spherics and VLF transmitters. These amplitude nulls are circled in Figure 1. In his analysis, Steve investigated if summation of two signals 180 degrees apart in phase could be one of the dominant modes in the observed data. In Figure 3, Steve modeled two sine waves. One shifted 180 degrees in phase and plotted the results in the top plot. The bottom plot is his observed amplitude and phase data of WWV, showing extremely strong agreement. On the right is a schematic that he drew up of day and nighttime propagation, illustrating the change in waveguide mode due to daytime delayer. Enthusiasts that observe transient luminous events use GNSS timestamp photography to capture sprites, halos, and other TLEs, often called mesospheric lightning. This is an example of a sprite caused by 157 kiloamp lightning stroke on February 28, 2024, captured by TLA enthusiast Frankie Lucina that occurred in a storm off the coast of Puerto Rico. The image on top right is Frankie's image capture of the sprite, and the bottom shows a satellite imagery of the storm. On the right shows a stacked time domain, time domain plots of the spheric at different VLF receivers in Europe and the one in Springbrook Township. The oscillatory component after the impulse is the ELF slow tail, a characteristic of continuing current strokes that can create TLEs. The benefit of GNSS time stamping allows correlation of spherics with time-stamped photography. On September 20, 2023, visible aurora was observed in Pennsylvania. This aurora caused scintillation in GNSS signals, which created a reduced availability of GNSS. Because the absolute phase measurement of NAA utilizes the GNSS pulse per second signal as a reference, the error in the timing solution created this sawtooth pattern in the carrier phase measurement, which is the top plot. Small scale amplitude variation from 130 to 6 UT is also indicative of aurora. As a bonus, an indicator of solar activity due to a solar flare, a large SID occurred that day at around 1400 UT, along with some smaller ones. Overall, this was quite an amazing observation. VLF-RX Tools is a multi-purpose SDR toolset, can be used for many different applications. In this application, VLF-RX Tools is used as an alternative software in an experiment for Grapevine, where many of its signal processing features and benefits can be utilized. One of the primary benefits to use VLF-RX Tools software is the precise sample alignment and time stamping using GNS pulse per second, currently not present on the Grapevine. As you can see, there are two plots. One is a WWV carrier from a Grape DRF system on the left, and the other is the same signal captured by VLF-RX Tools. Credit to Graham for these plots. So to build this network, to make this network a success, we are looking for PIs and co-PIs looking to acquire high-quality VLF data and collaborate with HamSCI to help build the network. We're looking to funding to build the VLF receiver kits. Radio amateurs and volunteers willing to install a VLF receiver kit at their radio quiet location and upload data to a central server similar to the Grape. Also, to build their own kits if they wish. This is made possible with low-cost hardware and open-source software. And to perform simple maintenance to keep their VLF receivers operating properly. The cost is about $300 per kit. Collaboration with HamSCI and the University of Scranton, which is a very good thing. And these kits will be fielded by radio amateurs and volunteers willing to install their kit in a radio quiet location and upload to a central server. Strategic locations are welcome. Please contact me or Nathaniel if you are interested, although these kits are not available yet. We are looking for volunteers willing and excited to learn about the study and observation of VLF phenomena, looking for something highly technical, hands-on, and with unique engineering challenges, wanting to be at the cutting edge of science, exploring fascinating topics in the ionosphere and magnetosphere, and interested in contributing to a community of amateurs, other volunteers, and professional scientists to further advance collective knowledge. The benefits of this network, there will be a global network, a global VLF receiver network capturing and analyzing the VLF spectrum. We'll have a better understanding of the ionosphere and magnetosphere. We can use this network for lightning location, and it'll be the first ever HamSCI lightning location network. It can also allow understanding of VLF event footprints. So how big of a footprint can you observe whistlers and chorus, radio amateur and volunteer learning, and collaboration between amateurs and professional scientists. The outcomes of this network store a VLF spectrum data at each location, spheric and stroke solutions from the network to augment existing lightning location networks, a database of whistlers, dawn chorus, periodic emissions, and other events at each location, a database of SID events from worldwide military VLF transmitters. Thank you very much.
Great, thank you, Jonathan.